Okay, welcome everyone to another Thursday Science Lunch Talk. Today we have with us Evan Smith, who is a PhD student over at WVU. And today he'll be talking about spectral kurtosis for RFI mitigation, something that is very useful here with the Green Bank telescope. So whenever you're ready, take it away, Evan.
Thanks, Jesse. Thanks for inviting me. Spectral kurtosis is a statistical RFI flagging technique developed mostly by Gelunita and Gary. There's something Gary, I forget his first name. I've been working on this for a while. I gave a lunch talk about this 2 years ago at Green Bank. In the Drake Lounge, maybe 3. I worked on it a bit with Luke Hawkins and mostly now with Ryan Lynch. I don't know if he's here on the call, but I don't think so. But I've been working on this quite a bit in bits and pieces. Go on. Here's my cursor. So I said it's a statistical RFI detection. It works on primarily works on raw unaccumulated power values. That's a typo right there. Sorry. So for each channel in a certain like filter bank style data set, data is binned up into M raw spectra, and n equals d equals 1. That's just something. This is a basic thing I'll get to in a sec. And so for each channel, you have M power values, and you calculate these two sums, the sum of the power values and the sum of the squared power values. And with that, you calculate this SK estimator value. And there it is. Essentially, you'll get a value that is around 1, centered around 1 with some kind of distribution if you have clean data or just noise. And if you have RFI, then this SK estimator is going to be outside of those, outside of that distribution. It's kind of a measure of how it's not exactly the actual kurtosis of the data, which is the fourth moment, which is kind of how flat topped or kind of spiky a Gaussian distribution is. It's more of an estimator that works on power values instead of the actual channelized voltages. So there are these thresholds that are calculated by numerically solving for the PDF of this SK estimator shape, which is based on their values of M and N and D. And then you just numerically solve for the three sigma level kind of exclusion zone. If you have accumulated power values, so power spectra that have already been averaged, like a typical output of a Vegas spectral line mode observation, this N is going to become the number of spectra that went into that average. And then this D is a spectrometer shape parameter, which should be 1 for a FFT spectrometer, but it can be different based on if you have a different kind of programming or spectrometer setup. I don't really know too much about how that works. And I'll say again, feel free to ask questions during my talk. Just raise your hand. I have the participant list up right here, so you should like shoot to the top and I should be able to see that. I lost my cursor again. Here we go. Nope. Yeah. So recent development that I made into actually making it work is multiscale spectral kurtosis. So I will refer to this single scale SK or SSSK as what I described on the previous slide. But this is weak to certain signal characteristics, especially those with signals that have 50% duty cycle, or signals that have their carrier frequency not at the center of our spectrometer channel, or signals with a very high data rate, um, or signals that send a lot more symbols. They send a lot of symbols within M spectra. So the whole deal is that you can bin these S1 and S2 values into smaller rectangles. And these are some example shapes, so 2 by 1, 2 by 2, 4 by 2. So for example, a 2 by 1 multi-scale shape would be 2 channels and 1 time bin, and they kind of binned up like that, and you can calculate that SK estimator formula. And this has the effect of kind of blending duty cycles of different signals in nearby time frequency pixels, and it can push SK values of those RFI affected pixels away from 1 and help us flag it better. And you can do this is like a separate thing. You can just do it right on top of the single scale kurtosis. And then another word about replacing flag data. This is something that Ryan and I had a little bit of back and forth on. I figure out what works and what doesn't. We find, at least for the pulsar data that I'm about to explain, after each channel is flagged, the pipeline searches for unflagged data points in the said channel and the nearest 3 channels on either side. So we're looking for clean data. And if we don't see any clean data in those 7 channels, it just keeps on adding on progressively further and further adjacent channels. And then simply just compute the mean and standard deviation and make some Gaussian noise and insert that in replacement of the flagged pixels. Yep. So we are doing some tests on real data, and I finished this presentation like 10 minutes ago, so there's going to be 1 or 2 typos, but we have a bunch of data courtesy of Ryan Lynch, and I think it's B193721. I wrote down performed MS-SK on observations of pulsar blank because I went to go look it up and then I forgot to add it to the slide. But the data set that I'll be showing off in the next couple slides has a center frequency of 1500 megahertz, bandwidth of 800, 4,000 channels. So we have that frequency resolution and the time resolution per unaccumulated spectrum. And so this is the really raw data, and these data files are huge. So there's a lot to look through. But this is pretty much more or less the entire L-band range. And so some examples of the RFI that we have in it are Iridium global satellite communications, Bedford radar over North Carolina, a bunch of meteorological satellite signals, as well as all the GPS bands or L-band GPS frequencies, along with many more. So here's a zoomed in spectrogram of the Iridium RFI. On the vertical axis, we have channel rather than frequency, but this is around 1620 megahertz. And along the horizontal axis, we have a kind of a pseudo time axis. So you can see this RFI looks kind of like a tire track with our high time resolution data. And yeah, it looks pretty ugly. Definitely not a scientific signal there. And so with signal scale kurtosis and replacing the data with noise, we get something that looks like this. So a good amount of the data is flagged and taken out, kind of disappeared. And if I do, I also have a picture of multiscale kurtosis with a shape of 4 and 2. So that's 4 channels and 2 time bins, which is this. And so even more of the data is gone, but not all of it. And I like to flip back and forth between these two to kind of show the difference. Yeah. Here's some of the meteorological satellite RFI that I found in our data. This is the unflagged version. This is somewhere around like 1550 megahertz. This is with single scale kurtosis, which has almost no difference. There's like a little bit down near channel 1900 that gets flagged, and that's it. And then when I added the 4x2 multiscale kurtosis, we get quite a bit better. Still not perfect, but you can flip between these. Yeah, you get the picture. So let's just show off some of the spectrograms there. Some of the results we got from this. I will say that, like, what are we trying to get here with more effective RFI mitigation? Like, what's our metric for success? And for pulsar data, you'll find less candidates in a blind search through the data. And you also have, when you generate time of arrivals for single pulses, you'll get smaller residuals if you're flagging the RFI well and not flagging the scientific signals. And as far as that goes, we're still kind of currently pending meaningful results from that. So like I said before, these data sets are huge because it's just the raw data. So doing the data search pipeline and generating the TOAs takes a really long time. It can take up to a week or a couple weeks for this data. And like I showed before, single scale kurtosis mitigation has not been very effective by itself. And I've only recently really started playing around with a functional multi-scale kurtosis. But again, that looks quite a bit more promising. And also this part of the kind of scientific process depends a bit on Ryan Lynch because he is super experienced with the software and finding this stuff, and he's a little bit preoccupied right now, understandably. But something I can do by myself is simulate RFI signals and their mitigation, which is what I've mostly been focusing on the last couple weeks. So I've got a Python script, both a large scale one on our Green Bank computer Leibniz and a smaller one that I run on a Jupyter notebook on my laptop that can create RFI signals, embed it in noise, and do all the mitigation I need to do. So currently I can currently create RFI with various modulation or encoding types. So that's binary phase shift keying, quaternary phase shift keying, amplitude shift, frequency shift, and minimum shift keying. Am I using GNU Radio? Yes and no. I'm using it as, I've used it as inspiration or kind of troubleshooting in the past, but this is mostly written in just straight Python by hand. I will also say that I'm not super experienced with GNU Radio as well, so I'm not going to be sure that I'm doing the right thing.
So for those unexperienced, what exactly is GNU Radio?
GNU Radio is a software program, more or less, to pretty much does everything radio, and it's written kind of like a typical like FPGA programming you can make these flow charts of different functions and blocks, like a block chart, sorry. And you can, create signals and read signals and do everything you might want to do. And at the end, once you have your block chart, you can just press generate and it'll make a Python script for you. So it's fun stuff. Glenn Langston also uses it quite a bit as well. I don't see him here. I ramp up the amplitude from 0 to 1 over the course of the test observation. I can change the data rate and have any amount of symbols per second. I can change the duty cycle and the period of said duty cycle. And I can also change the M for spectral kurtosis, or how many spectra I'm looking at once, as well as the multiscale bin shape. And I compare this stuff with, I compare the kurtosis mitigation with a kind of true RFI mask. And that's just looking at a clean section of the generated data and just saying mean plus 4 standard deviation power value and just flag everything above that. And obviously that's not really a rigorous or super true RFI mask, but it kind of works as a comparison at a basic level. So 2 of the numbers I'm looking at after this are what percentage of data points flagged by the true mask are also flagged by kurtosis. And then the overflagging percentage, which is what percentage of data points that are not flagged by the true flagged are also flagged by kurtosis. So say that 10 times fast. So here's an example signal that I made, 20 kilosymbols per second. And this is just a 1-bit binary phase shift keyed signal. So it's 20 kilobits per second. And this is our, also say this is 100% duty cycle, and it's at the center of channel 120 here. So it's the carrier frequency lines up exactly with this center channel right here. So this is the unmitigated. And then I have the single scale flagged. So it flags 96% of the RFI as our comparison mask sees it, and it flags an extra 26%. So this isn't like a super rigorous metric, but it does work for comparing different RFI mitigation schema. But you can pretty much interpret it as a quarter of the data, a quarter of the pixels that are flagged by RFI are also extra flagged on top. So the idea is that we're trying to get this flagged percentage up to 100% and our overflagged percentage down to less than 3.5%, more or less. Obviously, uncertainties are a thing. And the 3.5% number comes from flagging noise on either side. So that's false positives. Where'd my cursor go? Yeah, okay. Now this is the same data set with a multi-scale bin size of 4 and 2. So 4 channels and 2 time bins. And it flags a little bit more of the RFI, but our overflag percentage is 183%. So that's almost twice as much of the original RFI is flagged on top of that. Or twice as much of the pixels are flagged that need to be, which isn't great. And here's a little bit, this is a little bit of a insight into what's going on underneath the hood. This is a scatter plot of the log power of our data power values and the kurtosis values. And I have marked out here on the legend our middle channel. So these are data points in the middle channel, 120. And then looking on channels on either side have different colors. So someone with more statistics knowledge than me or Ryan can maybe understand this, but it's apparent that as the signal gets stronger in the middle channel, our SK values kind of go lower than 1 and outside of our threshold, which is like 0.78 to 1.31, I think, if I remember correctly. So data points outside of these two dashed red lines are considered RFI, as Kurtosis sees it. So our middle channel kind of dips below our acceptable threshold, and the sideband channels kind of streak way up here, which is kind of fun and interesting to look at. I can also do the same thing for the multiscale values. Again, not super sure why these specific points follow where they're going, but our middle channel kind of dips up, and so does our sideband channels. And I also have down at the bottom noise, which is gray in this plot, and I think it was blue in the other. Now it's orange again. So you can see where our noise or clean data set is supposed to sit at low power and acceptable SK values. And there's no need to show you all the hundreds of spectrograms and scatter plots that I've made. So you can kind of go over some of the results that I've found. So for RFI that has a data rate, and this is only on binary phase shift keyed signals. I'm working on playing around with different kinds of encoding, but I'm not quite there yet. But for data rates less than 20 kilobits per second, both the single scale and multi-scale flag more than 90% of the data. It falls below 90% for faster data rates. It gets down to like the 60s or 30%, 60 to 30%. Even as low as 20%. But playing around with different M values, it tends to overflag for data rates less than 4 kilobits per second. And I think I have a typo there. But lower, yeah, it should be higher M. Wait, no, that makes sense, yeah. So higher M values overflag for slower data rates, and lower M overflags for higher data rates. Yeah, there's some talks. Yeah, I've looked into that, Stephen Harrison. Thanks for that. Haven't done too much work into that, but I've read the paper. Is the overflagging of the multiscale because it smears the neighboring channels, so it cross-contaminates it? Yes. That's more or less what's happening. I think there's a small caveat on that, but I think that's what's going on underneath the hood there. I also played around with having the carrier frequency of the channel of the signal not being at the direct center of the channel. And a single scale kurtosis is weak to that, but if you have a multi-scale kurtosis with a channel width of more than or equal to 2, can make up for some of that missing flagging without much overflagging overhead, but it's also kind of similarly weakened. So it can get down to like 70%, like 70 to 80% flagging rate. And so, yeah, and I wrote here for the carrier frequency at a channel center, multi-scale kurtosis with a channel width more than 1 or 2 can introduce significant overflagging. I got more than 500% on some of these experiments. And that's, I think it's just simulating, or it's kind of cross-contaminating and kind of smearing that kind of duty cycle out, or that signal out. I'm also, when I flag with multiscale, I should also say, when I flag with multiscale, it's I have these bins, these rolling bins going through my 2D array, right? And when I have a bin, one of those larger multiscale bins, detect RFI, I flag every pixel in that bin. So it's perhaps a little bit strict, but we can make it work. And again, signals with duty cycle around 50% are not well detected by single scale kurtosis. But as long as we have multiscale with a bin channel of more than one, you can definitely make that up without too much overflagging overhead. And then a fun thing with the center channel is not flagged with the single scale kurtosis, but the sidebands still are. So that's kind of an interesting thing. And doing multiscale kurtosis with a time bin width of more than one doesn't really significantly increase the flagging. It does increase flagging, but really marginally. And here's an example of the 60% duty cycle signal. Here it is unflagged, and then there it is with flags. So perhaps someone with, well, I understand why the center channel isn't getting flagged, but still not clear on why the sideband channels are still getting flagged as the signal gets stronger and stronger. And then with this is with MS shape of 2 and 1, so 2 channels and 1 time bin. So that gets that center channel and overflags at around 18%, which is okay. Maybe that's acceptable. Here's our scatter plots. You can see our single channel, even though it has really high power, our data values don't really leave our dashed red line, while the sideband channels still do. But with multiscale, they get kind of pushed up like this, and so they get flagged. I think I already said most of this. It's 12:45, so I'm gonna finish it up. Oh yeah, I'm also doing this as well. I've been putting together a spreadsheet of like all the satellite and terrestrial L-band possible RFI signals that we might be able to see in some of our data. And I'm just trying to collate it all in a big spreadsheet with some links to extra info, where the RFI is from, and like any kind of extra info like encoding or strength or bandwidth, stuff like that. Because I want to be able to eventually fill out this far side of the spreadsheet here and see what gets flagged by some of these various RFI mitigation techniques that I've been looking at and what doesn't. So yeah, that's the thing that I've been working on. So just to summarize, on our real pulsar data, figuring out our mitigation is slow but promising, and finding some of the simulations or simulated RFI data has yielded some results as far as relationships between RFI characteristics and kurtosis flagging. And that's faster data rate signals are less well flagged. Multi-scale kurtosis with at least 2 channels can flag much better than a single scale, and adding time bins doesn't really significantly improve flagging. Just a quick dash through some future work, working on getting publishable results on the real simulated data, both for a paper and for my thesis. As far as developing the kurtosis pipeline, plan on porting this to C++ so that it's faster and more optimized, and eventually use it with the GPUs. I also want to apply an optimized SIR, that stands for Scale Invariant Rank Operator algorithm, on top of the SK flags. This is just something that works on a mask, and it kind of like a Boolean mask, and kind of extends to adjacent channels. As far as the real data goes, I want to have time of arrivals, pulse time of arrivals generated for a range of multi-scale kurtosis bin shapes on the same data set. And just want to get an idea of what yields the best results given our green bank data and the RFI environment contained within. And as far as simulated data goes, there's still a wide range of RFI characteristics and SK mitigation schemes yet to test. I've only simulated our phase shift keyed signal, but I showed there was that list of different encoding types, which I think will be interesting to look at, and kind of just understand the statistics of what's really going on other than just what's a base level. And yeah, I think that's it. Go open it up for questions or discussion.
All right, fantastic. Thank you very much, Evan. So yeah, if anyone has questions, feel free to unmute themselves and ask away. But in the meantime, a question I had for you that you actually ended up touching on in this slide here is basically, how do you decide what binning configurations you've got? You talked about at the beginning, 2 to 1 or 3 to 4. How do you actually know which of those is best to use other than just running them all?
Well, through the simulations so far, I've gotten an idea of like what kind of works and what doesn't. Like I said, like adding. I want to get around to doing some wacky multi-scale sizes, but adding pixels to my multi-scale bin lengthwise along the time direction doesn't really seem to do much, which kind of makes sense because these RFIs, like a single RFI with a single duty cycle is going to be stretched along that time direction, right? So if you're blending pixels with the same signal in it, you're going to get the same signal, and Kurtosis still isn't going to see it, or it will, or it won't. So I think having at least like one extra channel helps a lot. I want to do like a multi-scale shape of like one channel and like 200 time bins to see what that looks like.
I guess it also depends on the type of RFI itself.
Right. Yeah, as far as like being a blind, like a blind RFI flagging thing, it's hard to say because, our 800 megahertz observations, they have the whole range. They've got the big, wide, bright GPS signals, the tire track, iridium. Yeah, lots of stuff.
This is related to something I would ask then. Does it run faster whenever you have the bin data? So if you're doing like a 2x2 grid, does that run faster than if you just do the 1x1?
It's I mean,
or is it pretty comparable?
Theoretically, it's probably pretty comparable. A lot of the computing work goes into I think a lot of the computing work just goes into like creating those S1 and S2 arrays and then going through each channel. It's written right now so that the pipeline is written right now so that like the S1 and S2 arrays that are generated for the single scale just go right into the multi-scale without being without having to be like recalculated or anything. So that probably takes out a bunch of overhead as far as multi-scale goes.
Okay, so if you have a mix of different types of signals, broadband signals, really narrow band, it wouldn't be too much slower to run a single scale and then a multi-scale, let's say, would it? Because you already are making those masks.
Right. It probably won't be too much to what was I going to say? It probably wouldn't be too much to do several multiscale bin sizes too at the same time, or one right after the other.
Okay. Like if you know that in your range you have a few different signals, types of signals, and this mask works good for this type of signal and this mask for another. So sort of a hybrid
Right.
approach. Okay. That answers my question then. Thank you.
Now, would the ultimate goal here be to create, a system that flags these actively in data, or would you be creating a database with known RFI signals and masks for them?
Why not both? I mean, the dream for this is to, and this has been written about by Anita and others. The dream would be, like I said, porting it to C++ and for using it with a GPU / FPGA. For this, like I go back to the, where my cursor went, back to the original equation. Like this is really fast and simple to do.
Okay.
And if you were able to do this, if you're able to parallelize it, that was a word. If you're able to do that, you would be able to put that inside of a spectrometer and just have it flagging on the raw spectra before anything gets accumulated or output by the spectrometer. So that would be the dream.
Especially with signals constantly, new signals popping up.
Yeah. So like if you were taking some H1 data of a galaxy in L band and the GPS L3 signal fires at 1381, and you can just click like a Vegas config file. You just say kurtosis equals true. And you can just have that, and then inside Vegas, it will just see the RFI and flag it out. And then just replace it with noise and give you cleaner data. That would be the dream.
Do you think there is going to be a limit on time resolution for what this is going to be able to keep up with? Or if you just throw more hardware at it, eventually you'll be able to keep up with anything?
I don't see why not. Although I'm not, firmware genius.
So early in your slides, you showed some real RFI data, and you're talking about using multi-scale spectral kurtosis on these contiguous pixels. But in the RFI, you were showing there were streaks on non-contiguous channels that were clearly time correlated. I was wondering if your program could look for those time correlations and maybe improve the flagging percentage. Do you do that already, or would that be helpful?
Are you talking about these vertical bars?
That, yeah, and I think on the, in particular, I think it was the previous slide, or a couple, yeah, these guys. Yeah, so there's these streaks in these non-contiguous channels. They're clearly time correlated. I was wondering if you could maybe use time correlation between those streaks to better identify which of those peaks is RFI.
That would be a clever thing to do, yeah. That's a really good idea. I will say for this data, this isn't actually a scientific file. I accidentally ran this on pretty much an observation of the low noise Cal diode of Vegas. So that's what the bars are here. Yeah. So technically there is a pulsar here, but it's, there's a cal diode in the way.
Okay, well, it's almost 1 o'clock, so I think we have time for maybe one more question if anyone has something they wanted to ask Evan about.
One more for me. In practice, this would be something that you would want to be able to turn on and off, correct?
Yeah.
Okay, and it could be designed as such.
Yep. Cool. One last word. The advantage of this, which I've seen so far, still holds to be true. This kurtosis, this is obviously the whole L band spectrum. There's more of this is zoomed in, but this data set also contains neutral H1 from the Milky Way, obviously at 1421 megahertz, and kurtosis does not flag it, doesn't see it, which is the advantage of this. One of the big advantages of this method. It's not supposed to see scientific signals, or it's not supposed to see what's the word? When all the sine waves don't line up. I'm having a brain fart on that word. Incoherent light. It's not supposed to see that. Which is true of, Milky Way H1.
It's a pretty useful feature.
Yes.
All right, well, it's 1 o'clock, so we should probably cut this now. So everyone, give a big thank you to Evan one last time for giving us a talk about something that is super critical for the future of GBT. And finally, I'll just say that tune in next week where we will have a talk from Jaylee Hugh from UPenn. Thank you, everybody, and have a good rest of your week.